and I found the pseudocritical pressure and pseudocritical temperature of that mixture, I'm going to use the same law of corresponding state. I'm going to normalize my temperature and pressure of the system, this time by pseudocritical temperature and pseudocritical pressure, to obtain the pseudo-reduced pressure and pseudo-reduced temperature of the mixture. And then I can use these pseudo-reduced pressure and temperatures to find the Z factor for a mixture of the components that I have. Okay. So this figure 3.7, is actually graph that we are going to use. 3.7 and 3.7 and 3.8 are the graphs that we are going to use to calculate the Z values. And this is used for all the natural gases for a mixture of multiple components. So if I have a natural gas, basically a mixture of multiple components, then the mole fractions should come from the lab. So we know the mole fractions. If I know the mole fractions and I know the components, I can go to the end of the book, table A1, and for every component, I can read the critical temperature and critical pressure. These are fixed numbers for pure gases. Okay, so for example, for methane, for ethane, for propane, butane, pentane, all of them, they have every one of them, they have the fixed critical pressure and temperature that can be obtained from end of the book. So I'll get those from end of the book. I have the mole fractions, I multiply, and mole fractions by critical temperature of each component, I sum them up, that's my pseudocritical temperature. Okay, I used it to use this pseudocritical temperature to normalize the actual temperature to find the pseudo-reduced temperature. I'll do the same for pressure, and when I have the pseudo-reduced pressure and pseudo-reduced temperature, which is given, I can find the Z factor. Again, this graph, just make sure you understand, this graph is again in two parts, the upper part and the lower part, and it's divided by this white line which separates these two. So if your pseudo-reduced pressure is between 0 to 8, you are going to use the upper part. If it's more than 8, if it's more than 7 and less than 15, I'm going to use the lower part. So if my reduced pressure becomes 4, then I'm going to use the upper part. And then for the reduced temperatures, I have the numbers here. For example, if the reduced pressure is 4 and reduced temperature is 2, so I draw a line from 4, I'll go all the way to the 2, and then I read the Z factor from the left, which is 0.94. Okay. If the pseudo-reduced pressure is more than 7, let's say it's 10, and then my pseudo-reduced temperature is 1.3, then this is 10, I go up, and this is 1.3, then I can read the Z value, which is 1.17 or 1.18 from the right. Okay. So if the pseudo-reduced pressure is less than 8, I'll use the upper part. If it's more than 8, I'll use the lower part. And then the pseudo-reduced temperatures are given on the curves. Okay. If your pseudo-reduced pressure is more than 15, then you use figure 3.8. So if the pseudo-reduced pressure is more than 15, now I have pseudo-reduced temperatures. So if this 22 and then pseudo-reduced temperature is 1.6, so 22 and 1.6, I can read the Z factor, which is 1.8. Okay. So I'm going to use 3.7 and 3.8 for mixture of gases to come up with the Z factors. So I can get the Z factor of mixture of components using figure 3.7 and 3.8. I can find the upper molecular weight of mixtures. That's the summation of mole fractions times the molecular weight. And then I can use PV equal to ZnRT to calculate any property of the real gas mixtures. Okay. So let's do an example. So it says, in this example, it says calculate the mass in pound mole of the natural gas, which is given below, and contained in 43,560 cubic feet and 9,300 psi and 290 degree Fahrenheit. Okay. So it's like you have a gas in Utica shale. Okay. So to do that, what is given is the components. The components are given. The mole fraction of each component is given as well. So the first two columns, we know it. And we know these total pressure, total volume, and total temperature. So to solve this, the question is to find the mass. So I'm going to write the equation of a state, which says PV is equal to ZnRT. Okay. So it requires to find the pound mole. So I need to find the N So Pn is equal to PV divided by ZRT. P is the total pressure. I have it, 9,300. V is the total volume. I have 43,560. PV over R, which is 10.732, and T is 290 plus 460. What I don't know is the Z value. So if I know the Z value, I can simply find the N from the real gas equation of a state. So to find the Z value, what I need to do, since it's a mixture, I need to find the pseudo-reduced temperature and pseudo-reduced pressure to be able to find the Z factor. To find the pseudo-reduced pressure, I need to find the pseudo-critical pressure, because the pseudo-reduced pressure is simply the total pressure divided by pseudo-critical pressure. And to find the pseudo-reduced temperature, I need to find pseudo-critical temperature, which is the total temperature divided by pseudo-critical temperature. So the first step is to find the pseudo-critical temperature and pressure. Okay? The mole fractions are given. The critical temperature and critical pressure of all these pure components are given in table A. Okay? So we just need to convert that to Rankine. And these are fixed numbers. So from now on, if you want to know what is the critical temperature of methane, that's 343.3 degree Rankine. Done. Okay? So the critical temperatures and critical pressures comes from end of the book. Now if I want to find the pseudo-critical temperature, that's a mole fractions times the critical temperature. So mole fraction of each component times the critical temperature, and then I sum them up. That's my pseudo-critical temperature. The mole fraction of each component times the critical pressure, and I sum them up. That's my pseudo-critical pressure. So I got my pseudo-critical temperature and pseudo-critical pressure. Now I need to find pseudo-reduced temperature and pressure. So in step 2, I need to find the pseudo-reduced temperature and pressure. Pseudo-reduced temperature was the actual temperature, 290 plus 460, we converted to Rankine, divided by pseudo-critical temperature. And pseudo-reduced pressure is the actual pressure, which is 9,300, divided by pseudo-critical pressure, which is 665. So actual temperature divided by TPC, actual pressure divided by PPC, I'll get my values. So here, my pseudo-reduced pressure is 14, my TPR is 1.96. Okay, I need to find the Z value. So to find the Z value, I'll go and I check my Z chart. So 14 and 1.96. So 14, I know the PPR is 14, so I more than 8, so I'll go to the lower part. So 14, so I draw a line from 14 up, and the pseudo-critical temperature was 1.96, very close to 2. Okay, so this is 1.9, this is 2, so it becomes 1.35 roughly. Okay, so the actual value is 1.346. So with the rough estimation, I got a very close number. So I have the Z value, so PV equal to Z and RT, N is PV over ZRT, pressure is given, volume is given, R and T given, the Z we just calculated. So I can find the pound mole of the real gas mixture using the equation of state. Okay. So, so far what we have looked was the pure components. Okay. What if we have a mixture? We don't have a pure component, we have like heptane plus. If you remember in chapter 2, we said most of the time we report the gas component as the pure components like methane, ethane, propane, butane, pentane, and hexane. And then we lump all the components heavier than heptane, including heptane, and we call them C7 plus, okay, or heptane plus. So we don't really report all the components. We just report the volatile component all the way to C6, and then we sum the rest and we call them heptane plus. This is like whatever I have in heavier than C7 and including C7. So if that's the case, then we are going to use figure 310 to find their pseudo-critical pressure and pseudo-critical temperature. Because this heptane plus is not a pure component, I don't have the critical pressure and temperature of heptane plus at the end of the book. So what we are going to do, we are going to use figure 310. So if in your mixture you have heptane plus, then you need to use figure 310 to come up with their critical properties. So for that, you need to know the molecular weight and the specific gravity of heptane plus. These two information is always provided. So if you have heptane plus in your mixture, you do have the mole fraction of heptane plus, and also you will have the molecular weight and the specific gravity. You can use the molecular weight and the specific gravity of heptane plus to read the pseudo-critical pressure of the to read the critical pressure of the heptane plus and critical temperature of the heptane plus. And those two numbers can be used to find the total TPC and PPCs. An example says find the Z factor for a dry gas given below at the given pressure of 3810 and given temperature. It says properties of heptane plus are the specific gravity of 0.78, 0.758, and the apparent molecular weight of 128. So for heptane plus, the specific gravity and the apparent molecular weight is given. So again, the components we know, the mole fractions are given as well. So the critical temperature and critical pressure of all these components except C7 plus are given at the end of the book. Okay, these are constant numbers. So for any other example, you can use exactly these numbers, okay, for pure components because the critical temperature and pressures are fixed. However, for C7 plus, we need to find the critical temperature and critical pressure from figure 310. So if you remember, we said in figure 310, if you have heptane plus, you can find the critical pressure and critical temperature, knowing the molecular weight and the specific gravity. So here the molecular weight is 128, specific gravity is 0.76. So this is 100, 150, 128 is somewhere here, and 0.78 was 0.758. So 0.75, this is 0.8, so 0.758, so 100, 110, 20, 30, 40, 50, 128, and 0.758. So it's very close to 360, it's like 350 something. So 372 to be exact for the pressure. So for the pressure, like 372. For the temperature, again 120, 10, 20, 28, 0.78, 0.758. It's around 1100. So the actual number is 1082. So these two critical temperature and pressure of heptane plus can come from figure 310. So when we have that, then the TPC is simply the mole fractions times the critical temperature, sum them up. The PPC is mole fractions times the critical pressures, sum them up. And the TPR and PPR are the actual temperature normalized by TPC, actual pressure normalized by PPC. So PPC and TPC can be obtained by the summation of mole fractions times critical pressures and critical temperatures, and then TPR and PPR are simply the normalized temperature and pressure by TPC and PPC. So we have a TPR of 1.87, PPR of 5.7. So 5.7, let's say 1.9. And then I go to this graph. So it's 5.7, so it's less than 8. I go here. So this is 5, 5.5, 5.7. And it was 1.8, I guess. So if it was 1.8, then the Z value is very close to 0.95. So the Z value, obtained to be 0.96. Okay, so we have the Z value. Now that I have the Z value, I can calculate any properties like density, pound mole, viscosity, density, pound mole, specific volume, and any other properties of this mixture. Okay. So sometimes the components are not given, the mixture is not given, and instead the specific gravity of a mixture is given. So if the specific gravity of the mixture is given and you don't have the components, then you can use figure 311 to find the critical properties. But remember, this is for the case that you don't have the components. But in your class, and most of the time, we will have the components, so we will not use this graph.